when the universe defies explanation. Tonight, we're going to talk about something that keeps astronomers up at night. Not because they're scared, but because they're confused. Actually, genuinely confused. Because out there in space, we've discovered things that don't make sense. Things that shouldn't exist according to everything we know. Things that break the rules. And I'm not talking about science fiction. I'm not talking about theories or speculation. I'm talking about real observations. Things we've actually seen and measured. Things that are out there right now doing whatever strange thing they do, and we have no idea why. Over the past few decades, as our telescopes have gotten better and our ability to observe the universe has improved, we've stumbled across discoveries that have left scientists scratching their heads. Some of these discoveries challenge our understanding of physics. Some of them suggest there might be processes in the universe we don't know about yet. And some of them, well, some of them are just plain weird.
The wow signal, a 72-second mystery. Let me start with something that happened on August 15, 1977. A man named Jerry Ehman was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was part of SETI, the search for extraterrestrial intelligence. Every day it scanned the sky, listening for radio signals that might indicate intelligent life somewhere out there. Most days the data was boring, background noise from space, nothing unusual. But on this particular day, Ehman saw something that made him grab a red pen and write "wow" in the margin of the printout. That's why we call it the wow signal. The signal's characteristics. The signal lasted 72 seconds. During that time, it was 30 times stronger than the background noise. It came from a specific direction in the constellation Sagittarius. And here's what makes it so interesting. The signal's frequency was around 1420 megahertz. That's right near the hydrogen line, a natural frequency associated with hydrogen atoms. Why does that matter? Because hydrogen is the most common element in the universe. If you are an alien civilization trying to send a signal that other civilizations might recognize, you might choose a frequency related to hydrogen. It's like choosing a universal language based on something everyone would know. The Big Ear telescope had 2 receivers that scanned the same patch of sky 3 minutes apart. The signal showed up on the first receiver, but not the second. That means it lasted less than 3 minutes, probably closer to 72 seconds based on the data we have.
The search continues. Since 1977, astronomers have gone back to that same spot in the sky dozens of times. They've used more powerful telescopes. They've listened at the same frequency and nearby frequencies. They've searched for any sign of the signal returning. Nothing. The wow signal was a one-time event. Now, let me be clear about the uncertainty here. The signal could have been artificial or natural. The Big Ear telescope couldn't pinpoint locations precisely, so we know the general direction, but not the specific source. Proposed explanations. Some scientists have proposed natural explanations. Maybe it was a signal from a passing comet. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds. In 2016, a researcher named Antonio Paris suggested that 2 comets known as 266P Christensen and P2008Y2 were in that region of space at the time. But there's a problem with the comet theory. The signal was incredibly narrow band. It occupied a very specific frequency. Natural sources usually produce signals across a broader range of frequencies. The narrowness of the wow signal is more consistent with an artificial source, something deliberately transmitting on a chosen frequency. Other scientists have suggested it might have been interference from Earth, a satellite or aircraft, or some ground-based transmitter that happened to send a signal at just the right time. But the Big Ear telescope was designed to filter out terrestrial interference, and the signal came from a direction that was not consistent with any known satellite or aircraft at the time.
What it might mean. So what was it? Honestly,
it remains unexplained, and that's what makes it so fascinating. Nearly 50 years later, the WOW signal remains one of the most intriguing unexplained observations in the history of SETI. The fact that it never repeated is both frustrating and significant. If it was an alien civilization, why would they only transmit once? Maybe they were using a lighthouse strategy, sweeping a beam across the galaxy, and we just happened to catch it for a brief moment. Maybe it was a one-time broadcast. Maybe it wasn't meant for us at all, just an accidental spillover from some other communication. Or maybe it wasn't aliens at all. Maybe it was some natural phenomenon we don't understand yet. The universe is full of processes that emit radio waves: pulsars, quasars, magnetars, supernova remnants. We're constantly discovering new types of radio sources. Maybe the WOW signal was something natural that we've just never seen before or since. The truth is, the answer may never come. The signal lasted 72 seconds in 1977 and never came back. It's a mystery frozen in time. But it's also a reminder of how much remains unexplained about the universe. Somewhere out there in the direction of Sagittarius, something sent out a powerful, narrow-band radio signal, and we happened to catch it. That's either the most incredible coincidence in the history of astronomy, or it's evidence of something extraordinary. Either way, it's strange, and it's why almost 5 decades later, people are still talking about the WOW signal.
Additional SETI signals has detected, though it remains the most famous. In 2019, astronomers detected a series of fast radio bursts, or FRBs, that repeated at regular intervals, every 16.35 days, from a galaxy 500 million light-years away. While these are almost certainly natural phenomena, likely from a magnetar, they demonstrate that the universe is full of periodic radio sources we're only beginning to understand. There's also the curious case of BLC-1, Breakthrough Listen Candidate 1, detected in 2019 from the direction of Proxima Centauri, our nearest stellar neighbor. This signal also fell in a narrow frequency range that typically doesn't occur naturally. However, after extensive analysis, it was determined to be human-generated interference. The difference? We had better tools to analyze it and could observe it repeatedly. The WOW signal's uniqueness, its one-time appearance, its perfect characteristics, its mysterious origin, is what keeps it in the pantheon of unexplained phenomena.
Tabby's star, the dimming enigma. Now let's talk about something that's been happening right now. A star that's been driving astronomers crazy since 2011. Its official name is KIC 8462852, but most people call it Tabby's star, named after astronomer Tabitha Boyajian, who led the research team studying it. Tabby's star sits about 1,460 light-years away in the constellation Cygnus from Earth. It looks like an ordinary star. It's slightly larger and hotter than our Sun. Nothing about it should make it special. The discovery. But in 2011, the Kepler Space Telescope noticed something weird. Stars dim sometimes. That's normal. If a planet passes in front of a star from our perspective, the star's light drops slightly. That's how we detect exoplanets. When Earth passes in front of the Sun from another star's perspective, the Sun's light would dim by about 0.01%, tiny but measurable. Jupiter, being much larger, would cause the Sun to dim by about 1% if it passed in front. That's the kind of dimming we expect from planets: regular, predictable, small. Tabby's star doesn't do that. In 2011, its light dropped by 15%, then it came back. In 2013, it dropped by 22%, then it came back again. The dimmings were irregular. They didn't repeat at predictable intervals. They lasted different amounts of time. Sometimes the star would dim a little, sometimes a lot. The scale of the mystery. 22% is enormous. That's not a planet. A planet the size of Jupiter would only block 1% of the star's light. To block 22%, you'd need something absolutely massive, something as large as the star itself. The initial discovery set off a frenzy of theories.
What could be blocking the light?
The alien megastructure hypothesis. Here's where things got really interesting. Someone suggested it might be an alien megastructure. The idea comes from a hypothetical concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced civilization would do if it needed enormous amounts of energy. Eventually, he reasoned, they might build structures around their star to capture its energy output. Not a solid shell, which would be impossible, but a swarm of energy-collecting satellites orbiting the star. If you were building something like that, it would block varying amounts of the star's light as the structure orbited. It would be irregular. It would dim the star by large amounts. It would look exactly like what we were seeing with Tabby's star. Now, before you get too excited, let me be clear. Most astronomers don't think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here's the thing, we had to consider it because we couldn't explain the observations any other way. That's how weird this star is.
Natural explanations. So if it's not aliens, what is it? Scientists proposed several natural explanations. The comet swarm theory. Maybe there's a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, they would block light irregularly. Their dust tails would create uneven dimming. This was a leading theory for a while. But there are problems with the comet theory. Where did all these comets come from? You'd need an enormous number of them to block 22% of the star's light. And comets would produce dust, which would make the star appear redder when it's dimmed. Tabby's star doesn't do that. The color stays the same even when it's dimmed. The collision theory. Another theory suggested maybe there was a recent collision. If two large objects smash together near the star, the debris cloud could block light irregularly as it spreads out. But again, we'd expect to see excess infrared radiation from warm dust. We don't see that. Variable star theory. Some scientists suggested the dimming might be caused by the star itself. Maybe it's a variable star that dims naturally. But Tabby's star doesn't show the characteristics of known variable stars, and the dimming pattern is too irregular.
Recent observations. Then in 2017, astronomers made another observation. They caught Tabby's star dimming again and observed it across multiple wavelengths of light. What they found was interesting. The dimming was more pronounced in blue light than in red light. That's consistent with dust blocking the starlight. Small dust particles scatter blue light more effectively than red light. It's the same reason Earth's sky is blue. So maybe it is dust after all. But if it's dust, where's it coming from? Why is there so much of it? Why is the pattern so irregular? The current status. The latest observations suggest that Tabby's star might have a large debris field around it, perhaps from a destroyed planet or a massive collision or some other catastrophic event. The debris blocks light irregularly as it orbits. This is the current leading explanation, but it's not fully satisfying. The full picture remains unclear. And here's what makes this even stranger. Tabby's star is still doing it. We've now watched this star for more than a decade. It keeps dimming in weird, unpredictable ways. We have multiple data sets from different telescopes. The phenomenon is real. It's not a measurement error. It's not a glitch. Something is actually blocking the light from this star in ways that remain puzzling. As of 2025, Tabby's star remains one of the strangest objects in the sky. Out of hundreds of billions of stars, this is the only one that behaves like this. We've never seen anything else quite like it.
Other peculiar stars. Tabby's star isn't completely alone in its weirdness, though it remains the most extreme case. Astronomers have since found a few other stars with unusual dimming patterns. Boötes star 2, unofficially, another star showing irregular dimming, though not as dramatic as Tabby's star, was discovered in Kepler data in 2019. It dims by about 10% unpredictably.
VVV WIT08. This star, discovered in 2021, underwent an enormous dimming event, dropping to just 3% of its normal brightness. The event lasted nearly 200 days. Scientists think a large opaque disk or ring system passed in front of it, but the source remains mysterious. These discoveries suggest that whatever is happening with Tabby star might not be unique, just uniquely extreme. Perhaps there's a whole class of phenomena we're only beginning to recognize. Odd radio circles, cosmic mysteries in radio waves. Let me tell you about something that scientists discovered in 2019 that absolutely shouldn't exist. They're called odd radio circles, or ORCs. The name is perfect because they are odd, they're circles, and we only see them in radio wavelengths.
What are ORCs? Here's what they look like. If you point a radio telescope at certain parts of the sky, you see a perfect circle. The circle is enormous, hundreds of thousands of light years across. And here's the weird part. There's usually a galaxy at the center. The first one was discovered by a team led by astronomer Ray Norris. They were using the Australian Square Kilometre Array Pathfinder Telescope, or ASCAP, surveying the radio sky. ASCAP is sensitive to radio waves, which means it sees the universe differently than optical telescopes do. When the team processed their data, they found these circular structures. At first, they thought it was a processing error. Circles are suspicious in astronomy. Nature rarely makes perfect circles. But when they checked the data carefully, the circles were real. They found 3 more. Then other telescopes confirmed them. As of 2025, we found about a dozen ORCs. They're rare, they're large, and their origin remains a puzzle. Characteristics. Let me describe what we're seeing. Each ORC is a ring or shell of radio emission. The ring is nearly circular, sometimes perfectly so. At the center, there's usually an elliptical galaxy. The galaxy appears normal at optical wavelengths. There's nothing obvious about it that would explain the radio ring around it. The rings are enormous. Some are more than 1 million light years across. That's 10 times the diameter of the Milky Way. These are huge structures.
What they're not. Now, astronomers see circular things in the sky sometimes. Supernova remnants can look circular. They're the expanding shells of debris from exploded stars. But supernova remnants are much smaller, and they're associated with recent stellar explosions. ORCs are too large and too far away to be supernova remnants. Planetary nebulae can also look circular. These are the shells of gas shed by dying stars. But again, they're much smaller, and they're in our galaxy. ORCs are definitely not planetary nebulae. Some galaxies have radio lobes, where jets from a central black hole shoot matter out into space. These can create circular structures when viewed from certain angles. But ORCs don't match the characteristics of radio galaxies. The central galaxies don't show the active supermassive black holes that would be needed to create such structures. Proposed explanations. So what are they? Honestly, we don't know. Scientists have proposed several theories. Shockwave theory. Maybe they're shock waves from massive explosions in the center of galaxies. If a galaxy went through a period of intense star formation, or if its central black hole suddenly became active, it could create a blast wave that expands outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that's the case, why don't we see more of them? Galaxies go through active phases all the time. We should see these structures more often.
Galaxy merger theory. Another theory suggests they might be related to merging galaxies. When 2 galaxies collide, all sorts of crazy things happen. Maybe the collision creates shockwaves that expand outward as spherical shells. But again, galaxy mergers are common. ORCs are rare. Exotic explanations. Some scientists have suggested even more exotic explanations. Maybe they're the imprints of primordial events from the early universe.
Maybe they're related to cosmic strings or some other esoteric feature of spacetime. These ideas are pretty speculative.
Why they matter? The truth is, we're still in the discovery phase with orcs. We've only known about them for a few years. We need more observations. We need to find more of them. We need to study the galaxies at their centers in more detail. What makes orcs particularly fascinating is that they represent something new. We've been studying the radio sky for decades, but orcs only showed up when we built more sensitive radio telescopes. They were always there, we just couldn't see them until recently. This tells you something important about astronomy. The universe is full of things we haven't discovered yet. Not because they're hiding, but because we don't have the tools to see them. Every time we build a better telescope or observe in a new wavelength, we find something unexpected. Orcs are a perfect example. Nobody predicted them. Nobody was looking for giant radio circles around galaxies. They were a complete surprise. And now, astronomers are trying to figure out what they are and what they tell us about the universe.
Additional radio mysteries. ORCs aren't the only mysterious radio structures we've found. The universe seems to delight in creating circular or semicircular features in radio wavelengths. Radio relics. These are elongated structures in galaxy clusters, sometimes arc-shaped, created by shock waves from cluster mergers. But they're different from ORCs in size, shape, and context. The Fermi bubbles. Discovered in 2010, these are enormous gamma-ray and radio structures extending 25,000 light-years above and below the Milky Way's center. They're thought to be the result of a massive outburst from our galaxy's supermassive black hole millions of years ago. The E-Rosetta bubbles, even larger structures in X-rays discovered in 2020, also emanating from the Milky Way's center. These span more than 45,000 light-years. Each of these discoveries reminds us that the universe operates on scales and through processes we're only beginning to comprehend.
The giant arc and big ring, too large to exist. Now let's talk about something that breaks the rules on a truly cosmic scale. In 2021 and 2024, astronomers discovered two enormous structures that challenge one of the fundamental principles of cosmology. The giant arc. The first is called the giant arc. It was discovered by Alexia Lopez, a PhD student at the University of Central Lancashire. The giant arc is a structure of galaxies that spans about 3.3 billion light-years. That's not the distance to it, that's how large it is. The structure itself is 3.3 billion light-years across. To put that in perspective, light takes 3.3 billion years to travel from one end of this structure to the other. The entire observable universe is only 93 billion light-years across. This structure is a significant fraction of that. The giant arc is located about 9.2 billion light-years from Earth. It appears as a curved arrangement of galaxy clusters, like a giant arc in the sky, hence the name. The Big Ring. Then, in 2024, the same research team found something else. They call it the Big Ring. This is another enormous structure, about 1.3 billion light-years in diameter. It's also located about 9.2 billion light-years away. And here's the kicker. It's in the same region of the sky as the giant arc. So we have two enormous structures, both in the same part of the universe, both at the same distance. That's suspicious. It suggests they might be related somehow.
The cosmological principle. Now, why is this a problem? Let me explain. In cosmology, there's something called the cosmological principle. This principle states that when you look at the universe on large enough scales, it should be roughly uniform. No matter which direction you look, you should see roughly the same density of matter. The universe should be homogeneous and isotropic at large scales. This principle is fundamental to our understanding of the universe. It's built into the standard model of cosmology. It's supported by observations of the cosmic microwave background, which shows that the early universe was remarkably uniform. But the giant arc and the big ring challenge this principle. They're too large. According to calculations based on the Standard Model, structures shouldn't be able to grow larger than about 1.2 billion light-years. That's the theoretical limit based on how gravity has had time to pull matter together since the Big Bang. The giant arc is nearly 3 times larger than this limit. Even the big ring, at 1.3 billion light-years, is pushing the boundary.
Implications. If these structures are real, and they appear to be, then either our theoretical limit is wrong or something weird is going on. Maybe the cosmological principle doesn't hold as well as we thought. Maybe the universe is lumpier than we believed. Maybe there are processes we don't understand that can create structures larger than theory predicts. Some astronomers have questioned whether these structures are real or just statistical flukes. When you look at the distribution of galaxies, you can sometimes see patterns that aren't really there. Your brain looks for connections. You might see a line or arc of galaxies that's just a coincidence. But Alexia Lopez and her team did careful statistical analysis. The probability of the giant arc being a random arrangement is about 1 in 6,000. That's pretty low. The structure appears to be real. The big ring statistics are even more compelling, and the fact that both structures are in the same region of space makes a coincidence less likely.
So what are they? Baryonic, but never observed. If cosmic strings exist, they could create large-scale structures, as galaxies form preferentially along them. But cosmic strings are speculative. We have no direct evidence they exist. Incomplete cosmology. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we thought. Maybe the universe has large-scale structure that we didn't account for. Maybe at the largest scales, things are more complex than our models predict. This wouldn't mean the Big Bang theory is wrong. It would mean we need to refine our understanding of how structure formed in the universe. That's how science works. You make observations, build models, and when observations don't match models, you update the models.
The ongoing debate. As of 2025, the giant arc and the big ring remain controversial. Some astronomers are convinced they're real structures that challenge the cosmological principle. Others are more skeptical, thinking they might be statistical anomalies or misinterpretations of the data. What's clear is that the universe at the largest scales is more complex than we thought, and these enormous structures, whether they turn out to be real anomalies or something else, are pushing us to think harder about how the cosmos is organized. Other large-scale structures. These aren't the first large structures to challenge our understanding. The Sloan Great Wall. Discovered in 2003, this is a cosmic structure stretching 1.37 billion light-years, composed of galaxies arranged in a wall-like formation. The Hercules Corona Borealis Great Wall. Possibly the largest structure in the observable universe, this arrangement of galaxy clusters stretches about 10 billion light-years. Its existence is debated because it's so large it challenges the cosmological principle even more severely than the giant arc. The Cold Spot Supervoid. Associated with the CMB cold spot, which we'll discuss later, this is a region about 1.8 billion light-years across with fewer galaxies than expected. Each discovery pushes the boundaries of what we thought was possible in cosmic structure formation.
The Great Nothing. Let me tell you about a place in the universe that's almost empty. It's called the Boötes Void, and it's one of the strangest features of the cosmic landscape. Discovery and scale. The Boötes Void is a region of space about 330 million light-years across. To put that in perspective, that's more than 3,000 times the diameter of the Milky Way. It's an enormous volume of space. Here's what makes it strange. This volume should contain about 2,000 galaxies. That's what we'd expect based on the average density of galaxies in the universe. But when astronomers survey the Boötes Void, they find only about 60 galaxies. The rest is empty. It's not completely empty. There are a few dozen galaxies scattered throughout, but compared to what should be there, it's remarkably void of matter. That's why we call it a void. The Boötes Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the distribution of galaxies and noticed this huge empty region in the constellation Boötes. Initially, they weren't sure if it was real or just an artifact of their survey. Maybe they had missed some galaxies. Maybe their detection methods weren't working properly in that region. But follow-up observations confirmed it. The void is real. There really is a huge bubble of space with almost no galaxies in it.
Voids in the cosmic web. Now, voids are not unusual in the universe. The large-scale structure of the cosmos resembles a cosmic web, filaments of galaxies surrounding voids. Most voids are tens of millions of light-years across. They're pretty common. But the Boötes Void is special. It's much larger than typical voids. It's one of the largest known supervoids in the nearby universe, and its existence raises questions about how structure formed in the cosmos. Formation. Here's the thing. The universe started out almost perfectly uniform. The cosmic microwave background shows us that at 380,000 years after the Big Bang, matter was spread almost evenly throughout space. There were tiny density variations, but they were incredibly small. Over time, gravity amplified these variations. Regions that were slightly denser attracted more matter and became even denser. Regions that were slightly less dense lost matter to their surroundings and became voids. Computer simulations of this process can reproduce the cosmic web we see today. Filaments, clusters, and voids all emerge naturally from gravity acting on the initial density variations. But the simulations also predict limits. Voids can only grow so large given the age of the universe and the strength of gravity. The Boötes Void is close to this limit. It's about as large as voids can theoretically get. That makes it interesting because it's an extreme example. It's testing our understanding of structure formation. If our models are correct, we shouldn't see voids much larger than the Boötes Void. If we do, it would suggest something is wrong with our models. So far, the Boötes Void fits within theoretical limits, but it's close to the edge, and that makes it worth studying carefully.
There's another interesting aspect to the Boötes Void. The few galaxies inside it are weird. Some of them are forming stars at unusually high rates. Some have unusual shapes or characteristics. It's like the isolation has affected them somehow. Think about it. If you're a galaxy in a dense region of space, you're constantly interacting with other galaxies. You're pulling on them gravitationally. Sometimes you collide and merge. You're exchanging gas. You're part of a busy neighborhood. But if you're a galaxy in the Boötes Void, you're alone. Your nearest neighbor might be millions of light years away. You're evolving in isolation without the gravitational harassment that galaxies in dense regions experience. This isolation might change how you evolve. Maybe you retain more gas because nobody is stripping it away. Maybe your star formation happens differently. Maybe you develop unusual characteristics. The galaxies in the Boötes Void give us a chance to study what happens to galaxies when they're isolated. It's a natural experiment that the universe has set up for us.
The fundamental question remains, why is the Boötes Void so empty? Why did this particular region of space end up with so few galaxies? The answer probably goes back to the initial conditions of the universe. This region must have started out with a slightly lower density than average. Over billions of years, gravity pulled matter out of the region toward denser areas, creating the void we see today. But why was this region less dense to begin with? That's a deeper question. It relates to whatever process created the initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally, by chance, you'd get a larger variation. The Boötes Void might be the result of one of these chance larger variations in the initial conditions. From quantum to cosmic. It's remarkable when you think about it. The emptiness we see in the Boötes Void today, 330 million light-years across, originated as a tiny quantum fluctuation in the first fraction of a second after the Big Bang. That microscopic variation has been amplified over 13.8 billion years into this enormous supervoid. The universe is strange like that. The smallest things can have the largest consequences given enough time.
Other notable voids. The Boötes Void has company. The local void. Our own cosmic neighborhood sits on the edge of a void about 150 million light-years across. We're in a relatively thin region between it and a dense supercluster. The Eridanus supervoid. Associated with the CMB cold spot, this void is about 1.8 billion light-years across. The Giant Void. About 1.5 billion light-years across, this is one of the largest known voids. Together, these empty regions account for about 80% of the universe's volume, while containing only a tiny fraction of its galaxies. The universe is mostly empty space, but some parts are emptier than others. The CMB cold spot, an anomaly in ancient light. Speaking of the early universe, let me tell you about one of the most peculiar features in the cosmic microwave background. It's called the CMB cold spot, and it's been puzzling cosmologists since 2003.
What is the cosmic microwave background? The cosmic microwave background, or CMB, is the afterglow of the Big Bang. When the universe was 380,000 years old, it cooled enough that electrons and protons could combine to form neutral hydrogen. Before this, the universe was opaque. Photons couldn't travel far before hitting free electrons. After this, the universe became transparent. Photons could travel freely. The CMB is made of these photons. They've been traveling through space for 13.8 billion years. We see them today as a faint microwave glow coming from all directions in the sky. The remarkable uniformity. The remarkable thing about the CMB is how uniform it is. If you measure its temperature in different directions, it's almost exactly the same everywhere, about 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations. Some regions are slightly warmer, some slightly cooler. The temperature differences are about 1 part in 100,000. These variations are the imprints of density fluctuations in the early universe. Regions that were slightly denser were slightly cooler in the CMB. These dense regions eventually became the galaxies and galaxy clusters we see today. So the CMB is incredibly important. It's a snapshot of the universe when it was just 380,000 years old. By studying the pattern of hot and cold spots, we can learn about the initial conditions of the universe.
Discovery of the cold spot. Satellites like COBE, WAMP, and Planck have mapped the CMB in exquisite detail. And when scientists analyzed these maps, they found something unexpected. There's a region of the sky about 10 degrees across that's significantly cooler than expected. This is the CMB cold spot. It's not just a little bit cooler, it's about 70 millionths of a degree cooler than the average. That might sound small, but in the context of the CMB's tiny variations, it's huge. The cold spot is located in the constellation Eridanus. It's oval-shaped, spanning about 10 degrees by 5 degrees. That's roughly 50 times the apparent size of the full moon. Why it's strange? Here's why it's strange. Based on our standard model of cosmology, we can calculate the probability of such a large cold region appearing by chance. The probability is about 2.
Proposed explanations. Scientists have proposed several explanations. The supervoid theory. One idea is that the cold spot is caused by a supervoid. Remember, voids are regions of space with few galaxies. If there's an enormous void between us and the CMB in this direction, photons passing through it would lose energy due to something called the integrated Sachs-Wolf effect. Here's how it works. As photons enter a void, they climb out of a gravitational well, losing energy. As they leave the void, they fall into a gravitational well, gaining energy. If the universe weren't expanding, these effects would cancel out. But because the universe is expanding, the void gets larger and less dense while the photons are crossing it. This means they gain less energy on the way out than they lost on the way in. Net result, the photons end up cooler. So a supervoid could create a cold spot in the CMB. And indeed, astronomers have found evidence of a large void in the direction of the cold spot. It's not as large as the Boötes Void, but it's still substantial. But here's the problem. Even with this void, the calculations suggest it can only account for a small part of the cold spot's coldness. You'd need an absolutely enormous void to explain the full effect, and we don't see evidence of a void that large.
Multiverse collision. Another theory suggests the cold spot might be related to a collision between our universe and another universe in a multiverse scenario. In some versions of cosmic inflation theory, our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early on, it would leave a mark in the CMB, a circular region that's colder or warmer than average. This is a pretty exotic explanation, and there's no direct evidence for it beyond the cold spot itself. But it shows how puzzled scientists are. They're willing to consider multiverse collisions because the conventional explanations don't quite work. Statistical fluke. A third possibility is that the cold spot is just a statistical fluke. 2% probability means it's rare but not impossible. Maybe we just happen to live in a universe where this unlikely feature exists. Sometimes rare things happen. The challenge is that we only have one CMB to observe. We can't run the experiment again. We can't create 100 universes and see how many have cold spots. We have one data point, the universe we live in. This makes it hard to know if the cold spot is a meaningful anomaly or just chance. If we had 10 universes to observe and 9 of them had no cold spot, we could say with confidence that the cold spot in our universe is significant. But we don't have that luxury.
Current status. As of 2025, the CMB cold spot remains unexplained. It might be caused by a supervoid, but probably not entirely. It might be a statistical fluke, but that seems unsatisfying. It might be evidence of exotic physics, but that's highly speculative. What's clear is that it's anomalous. It stands out in the CMB maps. It's larger and colder than our models predict. And until we have a convincing explanation, it remains one of the strange things in our universe that we don't fully understand. Other CMB anomalies. The cold spot isn't the only peculiarity in the CMB. The axis of evil, not as sinister as it sounds, this refers to an unexpected alignment of the largest scale temperature variations in the CMB. They seem to align with the plane of our solar system and the ecliptic, which is bizarre because the CMB comes from when the solar system didn't exist. This might be a statistical fluke or a sign of systematic errors in our measurements. Hemispherical asymmetry. The CMB appears slightly different in opposite hemispheres of the sky. One hemisphere has slightly larger temperature fluctuations than the other. This shouldn't happen in a universe that's supposed to be statistically uniform in all directions. The low quadruple. The CMB's temperature variations at the largest angular scales are smaller than predicted. No one knows why. Each of these anomalies could be a statistical fluctuation, a measurement error, or a sign of new physics. Together, they suggest the early universe might have been more complex than our simplest models assume.
Przybylski's star, the radioactive enigma. Now, let's talk about a star that breaks the rules of nuclear physics, or at least seems to. It's called Przybylski's star, officially designated HD 101065. It's located about 370 light-years away in the constellation Centaurus. Initial appearance. From a distance, Przybylski's star looks normal. It's an A-type star, about twice as massive as the Sun and about 6 times more luminous. Nothing unusual there.
But when astronomers analyzed its light spectrum, they found something absolutely bizarre. The star contains elements that shouldn't exist in any star for more than a few weeks. Specifically, it contains technetium, promethium, and other radioactive elements with short half-lives.
The problem. Let me explain why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. In the most massive stars, the process continues, creating heavier and heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, the incredible pressures and temperatures create these heavy elements. They're scattered into space where they can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed. The star was born from a cloud of gas that contained material from previous generations of stars, including their heavy elements. Radioactive elements. But here's the catch. Some heavy elements are radioactive. They decay over time. Uranium, for example, has a half-life of about 4.5 billion years. That means half of any uranium will decay into lighter elements in 4.5 billion years. But even after billions of years, some uranium is still around. Technetium, on the other hand, has no stable isotopes. All forms of technetium are radioactive. The longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That's nothing on cosmic timescales. Przybylski's star is probably several billion years old. Based on its characteristics, it's a mature star, not a young one. If it formed with technetium in its atmosphere, that technetium would have decayed away billions of years ago. There should be none left. Yet, when astronomers observe the star's spectrum, they see clear evidence of technetium. They also see promethium, another radioactive element with a short half-life. And they've seen these elements consistently since the star was first studied in detail in the 1960s.
Possible explanations. So where is this technetium coming from? There are a few possibilities, none of them completely satisfying. Surface nuclear processes. One idea is that the star is creating technetium on its surface through some unknown nuclear process. Maybe there's a mechanism we don't understand that can produce these elements in the star's atmosphere, but this seems unlikely. We have a pretty good understanding of nuclear physics, and there's no known process that could do this in the cool outer layers of a star. Convection from the interior. Another idea is that the technetium is being brought up from the star's interior. Maybe deep inside the star, nuclear reactions are creating technetium, and convection currents are carrying it to the surface. But again, this doesn't quite work. The star's interior isn't hot enough to create technetium through normal nuclear reactions. Super heavy elements. A third idea, which sounds like science fiction, is that the star contains super heavy elements, elements with atomic numbers far beyond anything we've seen. In theoretical nuclear physics, there's something called the island of stability. The idea is that if you go far enough up the periodic table, beyond the known elements, you might find a region where certain super heavy elements are relatively stable. Some of these super heavy elements, if they exist, might decay into technetium or promethium as intermediate products. So the star might contain super heavy elements that are slowly decaying, replenishing the supply of technetium and promethium. This is highly speculative. We've never observed super heavy elements in nature. We've created a few in particle accelerators, but they decay almost instantly. The island of stability is a theoretical prediction, not an established fact. Still, Przybylski's star is so weird that astronomers are willing to consider exotic explanations.
Chemical peculiarity. Another strange thing about the star is its composition. It has unusually high amounts of certain rare earth elements. Its spectrum shows strong lines of elements like Hol.
The magnetic field is so powerful it would rip the iron from your blood at a distance of 1,000 kilometers. Your atoms would elongate, your molecular bonds would snap like rubber bands stretched beyond breaking. And this object, this impossibly dense cosmic monster, is spinning 700 times per second, releasing more energy in a single tenth of a second than our sun produces in 100,000 years. Welcome to the magnetar. Right now, scattered across our galaxy, there are objects so extreme they shouldn't exist according to our understanding of physics just 50 years ago. They're called magnetars, and they represent nature pushed to its absolute breaking point. These are not black holes, they're not quasars, they're something far stranger. The collapsed cores of massive stars, crushed into spheres just 20 kilometers across, yet containing more mass than our entire sun, wrapped in magnetic fields a quadrillion times stronger than Earth's.
But here's what keeps astrophysicists awake at night. We don't fully understand how these magnetic fields form. We don't know why magnetars behave the way they do. And most terrifying of all, we've detected magnetar flares so powerful they've affected Earth's atmosphere from 50,000 light years away. The stakes? Understanding magnetars means understanding the limits of matter itself, the nature of magnetic fields in extreme conditions, and potentially whether these objects pose a threat we haven't yet appreciated.
Today, we're diving into magnetars, the most magnetic objects in the known universe. These stellar remnants are so extreme that observing them is rewriting our understanding of physics, matter, and the violent life cycles of stars. But first, I want you to think about something. If a magnetar existed within our solar system, at what distance do you think it would become dangerous to Earth? Would it need to be closer than Mars, Jupiter, Neptune? Or could it threaten us from the outer reaches of our solar system, billions of kilometers away? Hold that thought. We'll return to this question at the end, and I think the answer will genuinely surprise you. It certainly surprised the scientists who first calculated it. Because magnetars aren't just fascinating cosmic curiosities, they're laboratories of extreme physics, testing the boundaries of what matter can withstand, and they're far more connected to Earth than you might imagine. Let's start with the basics, because understanding magnetars requires understanding what happens when massive stars die. When a star at least 8 times more massive than our sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in less than a second. Imagine an object the size of Earth compressed to the size of a city. This catastrophic implosion releases a shockwave that tears the star apart in what we call a supernova, briefly outshining entire galaxies. But the core remains, and what's left is a neutron star. Neutron stars are objects so dense that a single teaspoon of their material would weigh approximately 6 billion tons on Earth, roughly the weight of all humans on Earth combined, compressed into something the size of a sugar cube. They're composed almost entirely of neutrons, packed so tightly that atomic structure as we know it ceases to exist. The gravity at their surface is 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you would be flattened to less than a millimeter thick.
Now, here's where it gets interesting. All neutron stars have magnetic fields. Earth has a magnetic field, the one that makes compass needles point north. The sun has a much stronger one. But a typical neutron star's magnetic field is about 1 trillion times stronger than Earth's. Magnetars? They're neutron stars whose magnetic fields are 1,000 times stronger still. We're talking about magnetic fields measuring between 100 billion and 1 quadrillion times Earth's magnetic field. These aren't just strong magnets, they're the strongest magnetic fields in the entire observable universe. To put this in perspective, the most powerful magnets humans have ever created in laboratories using enormous amounts of energy reach about 45 Tesla. Earth's magnetic field is 0.00005 Tesla. A magnetar's surface magnetic field measures around 100 million to 1 billion Tesla. At these field strengths, the laws of physics start behaving very strangely indeed.
The story of magnetars begins not with magnetars themselves, but with a puzzle that emerged in the late 1970s. On March 5, 1979, at 10:51 a.m. GMT, satellites orbiting Earth detected something extraordinary. A blast of gamma rays, the most energetic form of light, struck our planet's upper atmosphere with such intensity that it knocked out several satellites and disrupted radio communications worldwide. The burst lasted only a fraction of a second, but it deposited more energy in Earth's ionosphere than had ever been recorded from a cosmic source. The source? An object 200,000 light-years away in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Scientists named it SGR 0526-66, where SGR stands for Soft Gamma Repeater. Dr. Krisa Kuvaliotu, working at NASA's Marshall Space Flight Center, was among the first to realize these weren't ordinary neutron stars. Throughout the 1980s and early 1990s, her team tracked several SGRs and noticed something peculiar. These objects emitted repeated bursts of gamma rays, and between bursts, they were slowly spinning down, rotating more and more slowly over time. On March 19, 1998, Kuvaliotu and her colleagues published a groundbreaking paper in Nature. They had measured the spin-down rate of SGR 1806-20 with unprecedented precision using the Rossi X-ray Timing Explorer satellite. The numbers revealed something shocking. To spin down this quickly, the object had to have an extraordinarily powerful magnetic field, far stronger than any previously known neutron star. The term magnetar was coined by astronomers Robert Duncan and Christopher Thompson in 1992, based on theoretical work they'd been developing. They proposed that some neutron stars could be born with magnetic fields powerful enough to dominate their behavior completely. These wouldn't be normal neutron stars at all. They'd be magnetic dynamos, their fields so strong they could crack the neutron star's crust like an eggshell. But here was the paradox that puzzled everyone. Where did these magnetic fields come from? How could a collapsing star core generate a magnetic field 1,000 times stronger than other neutron stars? And more pressingly, what was causing these objects to explode with such terrifying energy? By the year 2000, astronomers had confirmed about half a dozen magnetars. Today, we know of approximately 30, though estimates suggest thousands could exist in our galaxy alone, most remaining dormant and undetected. Each discovery added to the mystery. These objects weren't behaving according to the standard neutron star model. They were hotter than they should be, they were more energetic than their rotation could explain, and their magnetic fields seemed to be doing something impossible, actively powering the star, preventing it from cooling down, and occasionally, for reasons no one fully understood, triggering titanic explosions. So, what exactly do we observe when we study magnetars? Let's examine the evidence, because it's both spectacular and deeply strange. Evidence number 1, the X-ray observations. Magnetars emit enormous amounts of X-ray radiation. The Chandra X-ray Observatory and the XMM Newton telescope have cataloged their emissions in exquisite detail. Unlike other neutron stars, which cool gradually over millions of years and fade from view, magnetars remain luminous far longer than they should. They're glowing with X-ray light at temperatures exceeding 10 million degrees Celsius, not from leftover heat from their formation, but from the decay of their magnetic fields. Think about that. The magnetic field itself is the power source. As these impossibly strong magnetic fields gradually weaken over thousands of years, they release energy as X-rays. This is like having a battery that powers itself by slowly disintegrating, except the energy output is greater than hundreds of nuclear power plants operating continuously. Evidence number 2, the spin-down measurements. Every magnetar rotates, and every magnetar is slowing down. Dr. Victoria Caspi at McGill University has led extensive studies using radio telescopes to measure these spin rates with extraordinary precision. One magnetar, SGR 1900 plus 14, completes a full rotation every 5.2 seconds. That might not sound fast, but remember, this is an object more massive than the Sun, compressed to the size of Manhattan, spinning completely around 5 times per minute. What's remarkable is how quickly these objects are decelerating. Measurements show magnetars losing rotational energy at rates 100 to 1,000 times faster than typical pulsars. The only explanation is that their magnetic fields are so powerful they're acting like cosmic brakes, extracting rotational energy and converting it into electromagnetic radiation. The mathematics is elegant and disturbing. The spin-down rate is directly proportional to the square of the magnetic field strength. When Kuviliotou's team calculated the field strength needed to explain SGR 1806-20's behavior, they arrived at numbers exceeding 10 to the 15 Gauss. That's 1 with 15 zeros, or 1 quadrillion times Earth's field.
Evidence number 3. The giant flares. On December 27, 2004, humanity witnessed the most powerful explosion observed from beyond our solar system in recorded history. A magnetar designated SGR 1806-20, located approximately 50,000 light-years away in the constellation Sagittarius, experienced what astronomers call a giant flare. The event lasted just 0.2 of a second, 0.2 seconds. In that fragment of time, the magnetar released more energy than the sun produces in 150,000 years. The radiation was so intense it ionized Earth's upper atmosphere, expanding the ionosphere and affecting radio communications, despite the object being halfway across the galaxy. Dr. Kevin Hurley at UC Berkeley coordinated a network of satellites that detected the flare. His analysis revealed something astonishing. The initial spike reached Earth with the intensity of 1/5 of the full moon's light, except it was in gamma rays, invisible to human eyes but registered by every satellite equipped to detect high-energy radiation in Earth's vicinity. If SGR 1806-20 had been located just 10 light-years away, roughly the distance to some of our nearest stars, the flare would have been intense enough to trigger a mass extinction event on Earth. The radiation would have destroyed our ozone layer, sterilized the surfaces exposed to the burst, and fundamentally altered our atmosphere's chemistry. Only 3 such giant flares have been definitively observed, in 1979, 1998, and 2004, but smaller outbursts, what astronomers call bursts and flares, occur far more frequently. Some magnetars can produce dozens of smaller eruptions in a single day.
Evidence number 5. The radio emissions and silence. Here's where it gets even stranger. Most neutron stars are pulsars. They emit regular beams of radio waves like cosmic lighthouses. But magnetars are typically radio silent. Their magnetic fields are so strong, they actually suppress radio emission through processes we're still working to understand. However, and this is crucial, some magnetars occasionally turn on as radio sources. In 2006, magnetar XTE J1810-197 suddenly began emitting radio pulses after years of silence. The Jodrell Bank Observatory in the UK monitored it continuously, watching as it brightened, evolved, and then faded back into radio silence over several years. This transient behavior suggests magnetars exist in different activity states, transitioning between them in response to their internal magnetic field evolution. It's as if these objects are alive, breathing, changing from day to day and year to year. But the evidence leaves us with profound questions. What triggers a giant flare? Why do some magnetars produce dozens of small bursts while others remain quiet for decades? And most pressingly, what's happening inside these objects that create fields powerful enough to crack their surfaces? To understand what makes magnetars so extreme, we need to dive into the physics of magnetic fields at densities where matter itself becomes exotic. The interior of a neutron star isn't uniform. It's layered, like a cosmic onion, each layer more bizarre than the last. At the surface, you have an iron crust, though calling it iron almost seems misleading. The atoms are crushed together so tightly that electron shells overlap, creating a lattice stronger than any material in human experience. This crust is about 1 kilometer thick. Below that, you reach the outer core, where neutrons flow in a superfluid, a quantum liquid with zero viscosity. Imagine water that never experiences friction, that flows forever without slowing. Now imagine that water is made of neutrons and is under pressures exceeding anything achievable in laboratories by factors of trillions. Deeper still, in the inner core, conditions become so extreme that quarks, the particles that make up neutrons and protons, might actually deconfine, forming a quark glue on plasma.
We're not certain this happens, but calculations suggest the central densities of neutron stars might exceed the threshold. At these densities, you're no longer dealing with atoms or even subatomic particles. You're at the fundamental level of quantum chromodynamics, the theory governing the strong nuclear force. Now add magnetic fields to this picture. Not just any magnetic fields, fields powerful enough that they contribute meaningfully to the star's structure. At magnetic field strengths above 100 billion Tesla, something remarkable happens. The energy stored in the magnetic field becomes comparable to the gravitational binding energy of the entire star.
What does this mean? It means the magnetic field isn't just a feature of the magnetar, it's part of what holds the magnetar together. The field lines thread through the neutron star's interior, tangling, twisting, storing enormous amounts of energy in their configuration. Dr. Christopher Thompson at the Canadian Institute for Theoretical Astrophysics has developed detailed models of this process. His calculations show that magnetic field lines inside a magnetar can become unstable, similar to how twisted rubber bands eventually snap. When these field lines rearrange themselves, an event called magnetic reconnection, they release staggering amounts of energy in fractions of a second. This is the mechanism behind magnetar flares. The crust of the neutron star, while incredibly strong, can't withstand the magnetic stresses indefinitely. Eventually, something gives. The crust fractures, creating a starquake that shifts the magnetic field configuration. That shift accelerates charged particles to nearly the speed of light, which then collide with photons and other particles, creating cascades of high-energy radiation, the gamma ray bursts we detect. But here's the truly unsettling implication. The energy released in these events isn't coming from the rotation of the star, unlike pulsars, and it's not from residual heat. It's coming from the gradual decay and rearrangement of the magnetic field itself. Magnetars are essentially bombs on extremely slow timers, occasionally releasing explosive bursts as their internal magnetic structure evolves.
Recent observations from the Neutron Star Interior Composition Explorer, NICER, mounted on the International Space Station since 2017, have provided unprecedented data on magnetar surface hotspots. Dr. Tolga Guver and his team at Istanbul University analyzed NICER data from magnetar 4U0142+61 and discovered that the hottest regions on the star's surface correspond exactly to where theoretical models predict the strongest magnetic field concentrations should exist. These hotspots are between 200 million and 300 million degrees Celsius, roughly 30 to 40 times hotter than the sun's core. The magnetic field at these locations is so intense, it affects the quantum vacuum itself, creating particle-antiparticle pairs that briefly flicker into existence before annihilating. The vacuum, it turns out, isn't empty when magnetic fields get this strong. It becomes a seething foam of virtual particles, contributing to the radiation we observe. Perhaps most fascinating is what these observations tell us about quantum electrodynamics in extreme conditions. In 2016, a team led by Dr. Roberto Tarola at the University of Padova published observations in Science that showed direct evidence of vacuum birefringence, the phenomenon where empty space, polarized by ultra-strong magnetic fields, begins to behave like a crystal, refracting light differently depending on its polarization. This was a prediction from quantum electrodynamics made in the 1930s by physicists like Werner Heisenberg, but it had never been observed directly until magnetars provided the extreme conditions necessary. In a very real sense, magnetars are natural laboratories, allowing us to test quantum physics in regimes we could never reach in human-made experiments. The implications stretch beyond pure physics. Understanding magnetic reconnection in magnetar crusts might help us understand solar flares and coronal mass ejections from the sun, events that, while millions of times weaker, can still disrupt satellites and power grids on Earth. The mathematics and physics are fundamentally similar, just scaled to different energy regimes.
So we have observations, we have evidence, we have measurements, but the fundamental question remains: how do magnetars form? Why do some neutron stars become magnetars while most don't? The answer, like so many things in astrophysics, begins with a theory that seems almost impossibly elegant, yet raises more questions than it answers. The leading explanation is called the dynamo mechanism, proposed in detail by Duncan and Thomson in a series of papers throughout the 1990s and refined continuously since. The idea is that magnetars are born in supernovae with specific conditions that amplify magnetic fields to extreme levels during the first 10 seconds of the neutron star's life. Here's how it might work. When the stellar core collapses, it's rotating rapidly, perhaps once every few milliseconds, or hundreds of times per second. It's also turbulent, with convection currents churning through the proto-neutron star. These violent motions of conducting material, remember, neutron star material conducts electricity despite being neutrons, can act as a dynamo, converting kinetic energy from rotation and convection into magnetic energy. In normal circumstances, this creates strong magnetic fields, the trillion Gauss fields we see in typical pulsars. But if conditions are just right, if the rotation is sufficiently rapid, if the convection is particularly vigorous, if the proto-neutron star remains hot and fluid for just slightly longer, the dynamo can amplify the field by factors of hundreds or thousands before the star solidifies. Dr. Jeremiah Ostraker at Columbia University likens it to a cosmic amplifier, briefly turned up to maximum volume. Once the field is established and the star cools and solidifies over minutes to hours, the magnetic field is frozen in, locked into the structure of the neutron star, unable to dissipate quickly. But there's a competing theory, championed by Dr. Sergei Popov at Moscow State University and others. This alternative suggests magnetars might not require special birth conditions at all. Instead, perhaps all neutron stars are born with fairly strong fields, and magnetars are simply the youngest ones. We're seeing them before their fields have had time to decay. This fossil field hypothesis proposes that what we call a magnetar is just a phase all neutron stars go through. Give it a few 100,000 years and the surface field strength decreases. The magnetar becomes a high-field pulsar. Eventually, it fades into a dim, slowly cooling stellar remnant.
Evidence for this comes from observations of magnetar ages. Using supernova remnant associations and kinematic studies, measuring how fast magnetars are moving through space and tracing their paths backward, researchers have estimated that most known magnetars are between 1,000 and 100,000 years old, extremely young by cosmic standards. Dr. Sandro Marighetti at INAF-IASF Milano conducted a comprehensive study published in 2008, cataloging every known magnetar and estimating their ages. His findings showed a clear pattern. Magnetars appear to be young objects, and there's a deficit of old magnetars. Either they evolve into something else, or they become undetectable as their fields weaken and their emission drops. Yet another model, proposed by Dr. Konstantinos Gorgouliatos at the University of Patras, suggests magnetic field evolution might be more complex than simple decay. His simulations show that magnetic fields can undergo dramatic reorganization events throughout a neutron star's life, sometimes temporarily increasing surface field strength, even as the overall field energy decreases. Under this model, magnetar-like activity might occur in bursts across a neutron star's lifetime, rather than being limited to youth. Which theory is correct? The honest answer is we don't know yet. Each has supporting evidence, and each faces challenges. What we need, and what several upcoming observatories are designed to provide, is a comprehensive census of neutron stars at all ages, measuring their magnetic fields, rotation rates, and emission properties to see how these parameters evolve over time.
The philosophical implications are intriguing. If magnetars are special only because they're young, then our galaxy's history is littered with millions of dead magnetars, dark, cold neutron stars whose fields have faded but whose extreme structure remains. If magnetars require special birth conditions, they might be rare, meaningful outliers teaching us about the diversity of supernova mechanisms. And here's a thought to consider. Could magnetar formation depend on the properties of the progenitor star? Recent work by Dr. Philip Podsiadlowski at Oxford University suggests that rapidly rotating, highly magnetic massive stars might be magnetar progenitors. These stars show surface magnetic fields thousands of times stronger than typical massive stars, and they seem to rotate faster as well. If this connection holds, then understanding magnetars means understanding stellar magnetism throughout stars' lives, not just at their deaths.
The story becomes one of magnetic fields being amplified, maintained, and transferred from main sequence stars to their collapsed remnants, a cosmic inheritance of magnetism spanning millions of years and ending in objects that push nature to its limits.
For a moment, let's assume we have it figured out. Magnetars form in special supernovae, their fields are amplified by dynamo action, they slowly spin down and fade over hundreds of thousands of years, occasionally producing flares as their crusts crack under magnetic stress. The theory is elegant, the observations fit, and we can predict their behavior reasonably well. Except, we can't. On April 28, 2020, astronomers detected something that shattered this comfortable narrative. The SWIFT satellite, designed to detect gamma-ray bursts from across the universe, registered an intense burst of X-rays from a source within our own galaxy. Within hours, multiple observatories had pinpointed the source, SGR 1935 plus 2154, a magnetar about 30,000 light-years away. But this wasn't just another magnetar flare. Along with the X-ray burst, radio telescopes detected something unprecedented, an intensely bright radio pulse lasting milliseconds, containing more energy in that brief flash than the sun emits in radio waves in several days. Dr. Sandro Marighetti's team at IASF Milano and Dr. Bing Zhang's group at the University of Nevada, Las Vegas independently confirmed it. This magnetar had just produced a fast radio burst, an FRB.
Fast radio bursts are one of astronomy's newest mysteries. First discovered in 2007, FRBs are millisecond duration pulses of radio energy originating from distant galaxies, sometimes billions of light-years away. Despite thousands of detections, their origin remained unknown. Theories ranged from colliding neutron stars to evaporating black holes to exotic physics we haven't discovered yet. Some scientists even speculated about alien civilizations, though that was always the most unlikely explanation. But here, for the first time, an FRB was caught in the act, associated directly with a magnetar in our own galaxy, with multiple independent instruments confirming the detection. The implications were staggering. If magnetars produce FRBs, then a mystery spanning 13 years and countless papers had just found a plausible solution. But it also meant magnetars were capable of something we didn't think they could do: generate coherent radio emission at energies far exceeding what theoretical models predicted. Dr. Christopher Bokenik at Caltech, using the STARE-2 array, Survey for Transient Astronomical Radio Emission, calculated the energy in the radio pulse, about 10 to the 34 ergs in milliseconds. To put this in perspective, that's comparable to the total energy output of the sun in several seconds, concentrated in radio frequencies and emitted in less than 1/100th of a second.
The mechanism remains unclear. The leading hypothesis involves magnetic reconnection events, the same processes that cause magnetar flares, accelerating charged particles to form relativistic jets or beams. These beams, focused by the magnetar's magnetic field, could produce the intense, brief radio emission we observe as FRBs. But here's the twist that keeps this from being a neat solution. Most magnetars don't produce FRBs. In fact, SGR 1935 plus 2154 itself has produced only a handful of FRB-like pulses, despite hundreds of smaller X-ray bursts. So while magnetars can produce FRBs, they don't always, and we don't know what distinguishes FRB-producing flares from the more common non-FRB flares. Moreover, not all FRBs can be magnetar flares. Some FRBs repeat regularly, with periodicities suggesting they're associated with binary star systems. Others are so energetic that even magnetars struggle to explain them. The magnetar-FRB connection solves part of the puzzle, but leaves major questions unanswered. And then there's the matter of SGR 0418 plus 5729. This magnetar, discovered in 2009, violates nearly everything we thought we knew. Observations by the Chandra X-ray Observatory and the XMM Newton telescope revealed an object producing typical magnetar-like bursts and showing typical magnetar spin-down rates, but with a measured surface magnetic field of only about 6 × 10⁻12 Gauss.
That's strong for a neutron star, certainly, but it's 100 to 1,000 times weaker than typical magnetars. It shouldn't be acting like a magnetar at all, yet it is. Dr. Nander Rea, investigating this anomaly, proposed that SGR 0418 plus 5729 might have a relatively weak surface field, but an extremely strong internal field, perhaps 100 times stronger deeper inside the star. The surface measurements only tell us what's happening in the outermost layers. The interior could be dramatically different. This would mean magnetar classification isn't about surface fields alone. It's about the total magnetic energy budget and how that field is configured throughout the star's interior. Two neutron stars could have similar surface fields, but completely different internal structures, leading to completely different behaviors. The comfortable theory we thought we had, it's incomplete. Magnetars are more diverse, more complex, and more mysterious than we realized even a few years ago.
Let's push deeper into the strangeness, because once you start examining magnetars closely, the implications spiral into increasingly mind-bending territory. Consider time itself. Einstein's general relativity tells us that strong gravitational and magnetic fields can warp spacetime. At the surface of a magnetar, both effects are extreme. Time runs about 30% slower at the surface compared to a distant observer, meaning if you could somehow survive near a magnetar surface for what felt like 10 seconds to you, 14 seconds would have passed for someone far away. But the magnetic field adds another layer. Recent calculations by Dr. Matthew Baring at Rice University suggest that the ultra-strong magnetic fields might create frame-dragging effects, twisting spacetime in complex ways as the magnetar rotates. The rotating magnetic field essentially drags spacetime around with it, creating a magnetosphere that's simultaneously an electromagnetic and a gravitational structure. If these calculations are correct, then near a magnetar, straight lines become curves, not just due to gravity, as near any massive object, but due to the magnetic field itself. A photon traveling toward the magnetar wouldn't follow a simple path. It would spiral, its trajectory bent by both spacetime curvature and quantum vacuum polarization from the magnetic field.